This is problem number 6. We have a couple of pictures up here. We have a side view of the collision happening and the top view. So basically you're looking at it from a tabletop, from a side point of view, and then this is from looking down from the top view in. All right, it says the figures are not necessarily drawn to scale, so let's keep that in mind. It says an incident ball A of mass 0.1 kilograms is sliding at 1.4 meters per second on a horizontal tabletop of negligible friction. So that's going to be good, negligible friction, as shown above. It makes a head-on collision with a target ball B of mass 0.5 kilograms at rest at the edge of the table. As a result of the collision, the incident ball, so ball A, rebounds sliding backwards. So now it's moving the opposite direction at 0.7 meters per second immediately after the collision. It says, part A, calculate the speed of the 0.5 kilogram target ball immediately after the collision. So here we go. We have ball B is going to be hit, and we would expect it to follow this parabolic path once it leaves the edge of the table. We know this is ball A with its initial velocity. I'm going to choose to the right to be positive. So that means the initial velocity of A is 1.4 meters per second. So I'll go ahead and write that. I'll say VA initially is a positive 1.4 meters per second, but VA final is a negative 0.7 meters per second because it says it's moving backwards. Okay? And so what I'm going to do is we're talking about a collision here. And remember, momentum is going to be conserved, and they're not going to necessarily stick together. So what I'm going to do is I'm going to go ahead and say, all right, MA times VA initial plus MB VB initial equals MA VA final plus MB VB final. Now notice I changed my subscripts. Well, Coach Barkley, you can't do that. Well, I can, and I did. So I changed it from 1 to A, 1 and 2 to A and B. So that's okay, right? That's just there to help me out. Remember, subscripts are there to help me out. So we know that the initial speed of this guy we already have right there. The initial speed, here you go. He's sitting at rest at the edge of the table. So ball B is at rest. We know the final. So what I'm going to do is I'm going to try to find the final velocity of ball B. Well, in order to do that, I need to subtract off the mass of A times velocity of A final. But if I do it to the right, I also have to do it to the left. And so I get mass of ball A times VA initial minus mass of A times VA final, and that's equal to MB VB final. And divide both sides by MB. And so that I get VB final is equal to, I'm going to go ahead and plug in, the mass of A is 0.1 kilogram times the initial velocity, which we said was 1.4 meters per second, minus 0.1 kilogram times a negative 0.7 meters per second because it goes in the opposite direction. And then I'm dividing by the mass of ball B, which is 0.5 kilogram. So if I do that, I should get that the velocity of ball B after the collision is 0.42 meters per second, and it's positive, which means it's moving to the right. Okay? And so that's the speed immediately after the collision. So let's look at the next part. It says the tabletop is 1.2 meters above a level horizontal floor. The target ball is projected horizontally. Okay, so it's basically the target ball is the one we hit. That's ball B. Okay, that's B, ball B. It's projected horizontally and initially strikes the floor at a horizontal displacement is D from the point of collision. Calculate the displacement D. Now, we know the tabletop is 1.2 meters above the level. So if I go back up here, this is 1.2 from here, from there to there, which it already says over here. All right, and so what I'm going to do is I'm going to use kinematics. I know that this thing is only moving in the X direction initially. So I know that the initial velocity in the Y direction for ball B is 0. I know that, I'm going to call it down as positive now. I know that delta Y is a positive 1.2 meters per second. And I know the acceleration in the Y direction is a positive 9.8 meters per second squared. So what I'm going to do is I'm going to find the time it takes for it to fall 1.2 meters. Okay, so there's just some kinematics. Once again, I'm going to write this down. So delta Y is a plus 1.2 meters. I know that the initial velocity in the Y direction is 0. That's horizontally. So there's no velocity in the Y direction. I know the acceleration in the Y direction is a positive 9.8 meters per second squared. I chose down to positive. So I'm going to use my favorite equation. So delta Y equals V initial Y delta t plus 1/2 a sub y delta t squared. We know the initial velocity is 0. So then I can then write this as delta y is equal to 1/2 a sub y delta t squared. I can then multiply both sides by 2, so I get 2 delta y is equal to a sub y delta t squared. You can divide both sides by a sub y now. And so then I'm going to come up here and I get that delta t is equal to 2 delta y all over a sub y square rooted. So now I'm going to plug in that's 2 times delta y of 1.2 meters all over acceleration, which is 9.8 meters per second squared. The meters will cancel, and then I'll square root that. So let me do that real quick. I got 2 times 1.2 divided by 9.8. I got 0.244897. I'm then going to square root that. And so I'm going to get 0.495. So 0.495 is the time, seconds. So that's my time interval in the air. Well, here's the thing. It's able to stay in the air for that long, and it travels at that speed leaving the table. So here's the table. It leaves the table with a velocity of 0.42 meters per second. So I'm going to use my favorite equation again. That's the initial velocity in the x direction. Remember, I know the acceleration in the x direction is 0, and now I know the time. I don't have to put x because time is independent of direction. Is 0.495 seconds. So like I said, I was going to use my favorite equation, but now in the x direction. So delta x equals v initial x delta t plus 1/2 acceleration in the x direction delta t squared. Once I'm in free fall, there's no acceleration in the x direction. So I get that delta x is equal to the v initial in the x direction, which is 0.42 meters per second, times my time interval of 0.495 seconds. And so if I take 0.42 times 0.495, I get 0.2079. So this is 0.2079 meters. And so that's the total displacement that the object goes while in the air. Now, what would be also a kind of cool thing is we know that it bounces back at 0.7. We could also figure out how far A will land from the table, because we know its initial velocity is 0.7 in the opposite direction. So we could also do that too. But basically, for part A, we get 0.42 meters per second. And then for part B, I got a distance of 0.2079 meters.